Hi, my name is Thiago and today I'll be giving you a quick presentation of the work we developed at the University of Campinas. In this paper, we present a practical laboratory approach on polymer melt flow rate and stress strain testing to teach undergraduate students how to measure important properties of molten and solid plastics. A total of 21 groups of students were involved with testing 4 grades of polypropylene, learning how to obtain and analyze the statistical tools parameters that are important for quality control, polymer processing, and material selection for engineering applications. Students perform melt flow rate or MFR tests using the ASM T1238 standard to measure the density of molten polymer, MFR itself, and the viscosity of the molten polymer, as well as tensile stress strain testing following ASTM D638 standard to obtain the stress strain curves and obtain the Young modulus, yield stress and strain, and also stress and strain at break. Here in figure 1, we can see a typical stress strain curve, while in figure 2 contains the curve for the polymer samples. All 4 grades exhibited the expected behavior, which is a typical curve for cold drawing with the reduction of the cross-section due to the necking phenomenon, as we can see in figure 2 in set B. And we can also observe the typical stress whitening the necking region due to the crazing phenomenon. All the data collected from the MFR and stress strain tests is compiled in figure 3. Figure 3a, we can see no statistical difference for the molten densities, all around 0.73 grams per cubic centimeter, while in 3b we can see the MFR results are very close to the supplier data, blue dashed lines for all samples. In 3C, we have similar viscosity for the 3 grades, although slightly lower for the high flow sample and higher viscosity for the low flow sample. Young modulus in figure 3D, while lower than those from the supplier datasheet, exhibits the same tendency for each sample. This disparity arises probably from the fact that the supplier reports the results of bending tests, parameters that might not be equivalent to the loading speeds used in our tensile testing. Yield strain stresses in figure 3E and 3F are for the most part good matches to supplier data, although data for the high-flow homopolymer sample shows a statistically lower yield stress, which might arise from experimental errors or a faulty batch. Strain and stress at break in figures 3G and 3H are statistically similar for all samples except for the high-flow homopolymer. In conclusion, simple experimental procedures at the undergraduate level were presented, allowing for a more in-depth teaching of how different mechanical and flow properties of polymers can be determined. The data collected was also suitable for the teachings of advanced statistical toolkits such as ANOVA. Thank you.